Hello, biologists. Let's talk about diffusion, osmosis, and active transport. And we'll also talk a little bit about something called facilitated diffusion or facilitated transport. But let's start off with diffusion. Diffusion is the natural movement of air molecules. Air molecules, as you see here, we're kind of riding an air molecule in the simulation, are always bouncing around, and here we're bouncing off the sides of the container, we run into other air molecules, and we're bouncing, bouncing, bouncing. Diffusion is the natural movement of molecules due to collisions. And you experience diffusion in your everyday life. If somebody's making cookies in the kitchen and then you smell them in the living room, some of the cookie molecules are moving into the air and then they're bouncing around, running into other air molecules and running into the walls of the house. And eventually they're moving their way by randomly moving around into your living room and you smell them, which is pretty cool because I like smelling cookies or soup or whatever's going on in the kitchen. Let's talk a little bit more about diffusion by looking at another model. I'm going to reset this here. These are a cartoon of water molecules, let's say in a glass of water. If I put a drop of dye here, we can see how diffusion happens in liquids as well. The dye kind of stays together for a while, but through those random moving around and collisions with other water molecules and the sides of the glass, they spread out. So if you put a drop of food coloring in a glass of water and you just let it sit and you don't let it stir, it'll kind of hang by itself in the corner for a while. But after a while, if you let it just sit, the whole glass will be the same color. It'll be evenly distributed, and that's because of diffusion. If you look at the path taken by several red dye molecules up here, these little red dots in the model, their motion can best be described as, I'll let you read the options and choose. We're going to look at how diffusion works in a cell by looking at how molecules travel when the concentrations outside the cell, this is a high concentration of carbon dioxide here outside the cell, and a low concentration inside the cell. I'm going to run the model and let you look at what happens. Pay attention to the CO2 bars here and here. See where it says CO2, that's carbon dioxide. We're going to pay attention to these two bars as the model runs. Some of these carbon dioxide molecules can cross the cell membrane here. They can diffuse, they're moving around randomly like we just talked about on the first page with the first couple models where you're riding the air molecule, and then we saw the drop of dye in the glass of water. These molecules are going to move around, and some of them are going to cross the cell membrane that we have here. And you can notice in the beginning we had a high concentration over here. This bar was up here, and we had a low concentration over here, but now they're more even. So the molecules move from an area of high concentration to an area of low concentration. Let's look at another example here. Let's make this low on one side and high on the other side. And so again, watch the bars here. You can see this bar on the inside of the cell, CO2 is high, and as some of those molecules bounce around and move across the cell membrane, they're kind of evening out. Some of these molecules are bouncing across this cell membrane too, but because there are more molecules over here, more of them are going this way over to the outside of the cell than are coming inside. The concentration always tends to even out, going from high to low. Let's do one more experiment here. Let's put in a low concentration of oxygen and a high concentration of oxygen out here. And let's see where if oxygen does the same thing as carbon dioxide. There's a high concentration over here and a low concentration over here. So both carbon dioxide and oxygen are high over here, and they're low over here to start with what's happening. You can see from the bars here, looking at the level of CO2 and O2, that they're evening out. Let's try running it the other way where we put a high concentration on the outside and see if that works too. Let's go high and high and low and low and see what happens there. So they're both high on the outside of the cell now, and they're moving across that membrane both ways. They're going both ways. Some of them on the inside are moving outside and some on the outside are moving inside, but there's more on the outside moving to the inside of the cell. Because concentration, again, always goes from high to low. Nature always wants everything to be even, so things will try to even out across the cell membrane. And that's how diffusion works in the cell. So remember, molecules, if they can diffuse across the cell membrane, they'll diffuse from high concentration to low concentration to even everything out. So I have a similar model set up here where we're going to diffuse across the cell membrane, but this time we can watch a single molecule. And we'll see a lot of these molecules, they're going from high to low across the cell membrane. They're going to the outside of the cell because that's where the lower concentration is. And we might see this cell diffuse, we might not. It might go across the cell membrane. It might not. Cells move randomly, and that's the whole point of watching our one little marked cell, is that it's always moving randomly. It doesn't know that it's supposed to go to the other side and even things out. Molecules just move randomly. And after a while, the cell comes to what's called equilibrium. That's where there's about the same concentration on both sides. The word equilibrium kind of has the word equal in it here. It's spelled a little bit differently than you use it in math, but it means the same thing. It means the concentrations on both sides will be just about equal. And that means, it doesn't mean that the molecules stop moving. It means the molecules moving from inside the cell to outside the cell are equal to the number of molecules moving from outside to inside, so that the rate they're moving in different directions is even. So when they equal out, when they're at equilibrium, when a cell is at equilibrium, and the molecules, the concentrations are at equilibrium, like say of carbon dioxide we're looking at right here, the molecules moving to one direction are equal to the number of molecules moving in the other direction. It doesn't mean they stop moving, it means they're moving in the same directions and the same amount. And that's called equilibrium. Now we're going to talk about a little bit about diffusion and the role of surface area. The reason you have all these little tiny sacs in your lungs called alveoli is to give your lungs more surface area so oxygen can diffuse across from the outside of your lungs to the inside of your lungs, which is really great. You want all that surface area because that makes things happen faster. Let's look really quickly here in a model when there's not a lot of surface area. Diffusion happens, but it doesn't happen very fast. Let's bump up the surface area a little bit. And you can see this is kind of like what the inside of your intestine looks like too. It has lots of little fingers to help you absorb food molecules so food can go back and forth in your intestines. You have little fingers in the inside of your intestines that help give it more surface area. And that extra surface area is to help diffusion happen faster, to help molecules travel across cell membranes even faster. Here we can make even more surface area. There's more zigzags here. And you can watch the concentration here get even faster. So the more surface area you have here, the faster things even out or come to equilibrium. So some molecules are too big to get across the cell membrane. You can see it's kind of like looks kind of like carpeting. And if you try to put a ping pong ball through some carpeting, it's not going to fit. These holes are pretty tiny. Plus there's some charges that are involved. So some cells need a little bit of help. So they use what's called a pore. And if they use a pore, it's called facilitated diffusion. They're getting a little help. That's called facilitation. If we look here, we can see these little blue molecules. They're water molecules, and they're trying to get across the cell membrane, but they're too big. They can't do it. They're too big and they're polar, so they need some help. Polar means they're charged. They're kind of like a little magnet. So let's give this cell membrane an aquapore. It's like a little specially designed kind of hole that's made by a particular molecule that helps water get through the cell membrane. And we like water to get through the cell membrane because our cells need water to function well. So it's good that water can go in and out. And the way that happens is we put in purposefully, your body puts in holes in the cell membrane using this protein that makes aquapores, or special holes for water. Aqua means water, and pore means something that you can go through that's porous. And so you can see water can diffuse much better when it has a pore. When something needs help getting across the cell membrane, but it doesn't use energy, it needs help, but it doesn't use energy, that's called facilitated diffusion. The aquapore facilitates the diffusion. It helps the water get across. But it's not, the cell's not using energy here. It's still, the water molecules are just kind of randomly wander around and bounce across the cell membrane. So this is facilitated diffusion using an aquapore. Most molecules that need an aquapore or need some kind of pore or some help are polar, because the inside of the cell membrane is non-polar and it doesn't really like molecules. Now that we've talked about facilitated transport or facilitated diffusion using aquapores, helping the water through with a special kind of hole in the cell, and we've talked about diffusion, that molecules bouncing around and sometimes they cross the cell membrane, let's talk about osmosis. Osmosis is a special kind of diffusion that's just water. So we're going to look at water move across the cell membrane here, and water likes to even things out. You can see that there's more water molecules over here, and there's fewer water molecules over here because it's a higher concentration of salt. Salt is represented by the little green and red molecules, or if you're colorblind, that's just all purple. The blue ones, there are fewer blue molecules over here. And let's see what happens. If we let this run, there's lots of aquapores. You can see the little gray kind of representations of aquapores in this cell membrane. You can see that the salt concentration on both sides is going to kind of even out after a while. And in order to do that, it kind of pushes on the cell membrane. If water is coming into the cell to even things out, it's pushing on the cell membrane, and that's osmotic pressure. So osmosis is the movement of water, the diffusion of water across the cell membrane. Osmosis is the diffusion of water. It's like regular diffusion, but if you say osmosis, you just mean the diffusion of water. It's the diffusion of just water. So an osmotic pressure means the pressure on the cell wall by water pushing on it. When the cell is expanding, more water is coming in to even out the amount of water inside and outside the cell. And that happens if water comes inside the cell, it's because the salt concentration is normally higher. If we run it the other way, if we put a high salt concentration out here and a low salt concentration out here, what do you think is going to happen? There's more water molecules out here. There's a higher concentration of water because there's a lower concentration of salt. And over here, there's a high concentration of salt, so a lower concentration of water. Remember, osmosis is the diffusion of water, and diffusion happens so that both sides will be even. If there's more water here and less water here, what do you think will happen? We'll let it run. If the cell is shrinking, why do you think it's shrinking? Where's the water going if the cell's getting smaller? The salt concentration you can see is starting to even out here. So we talked about osmosis and osmotic pressure. Now we're going to talk about active transport. That's when channels like this calcium transport channel have to use some ATP. They have to use energy. Diffusion and osmosis and facilitated transport have just happened because molecules are bouncing around and they didn't use energy. But active transport, like this calcium channel, they have to use some ATP. And so we'll give some high ATP concentration so this poor calcium channel can do its job. We'll make a high calcium concentration. We'll run load model, and we'll watch it run. So it's waiting for some calcium to come into the channel, and then it can't just go across by itself. It needs to use some energy. So it's waiting for ATP to get on there. And now ATP got transported to ADP. Okay, here's calcium. It's waiting for some ATP to just bounce in there. Oh, it got some ATP, so now the calcium can go across. So you see that if calcium wants to go across, calcium's charged, it can't go through the membrane, diffuse through the membrane on its own. It needs to use some energy from the cell. It needs to use ATP. That ATP binds, it turns into ADP, and then the calcium can go across. But only with energy does calcium cross the cell membrane. It needs some help, it needs some energy, it needs to use energy. So it's different than diffusion, osmosis, and facilitated transport that don't use energy. Active transport has to use energy, like this calcium channel here. So thanks, biologists, for watching. Remember, we talked about diffusion, the random movement of all molecules, osmosis, the random movement of water across a membrane. We talked about facilitated transport, that helps random movement by making a hole in the cell wall. And all those first three, diffusion, facilitated transport, and osmosis, don't use energy. But when we come over here to the calcium channel where it's moving a charged ion, like a positive or negative ion, then it's probably going to use energy. It's going to use some ATP. Thanks for watching.